Dear students, welcome to this class on firm competition. So today we're going to talk about how firms compete against each other. Now, till now, we have been studying these two extreme cases where there is either an infinite number of firms, which is generally the case under perfectly competitive markets, or there is just one firm. When there are an infinite number of firms, then you don't have to explicitly model firm competition. We kind of already know what's going to happen. Because there's an infinite number of firms, no firm will have any market power. So they have no way of determining prices, they become price takers. So there's no need to explicitly model how the firms are interacting among each other. All you need to do is to remember that the firms are price takers. They cannot change prices. And then on the other hand of the spectrum is monopolies. And when you have a monopoly, they are the only firm in the market. And being the only firm, there's no need to think about competition. There's no need to ever model competition per se. Now, the first observation that brings us to the topic of this class is that, of course, there can be cases in between having just one firm in the market and having an infinite number of firms in the market. For example, how should we think about firm competition if there are just two firms in the market? This is quite natural. You can definitely think about cases where there are two or three major operators in the market. You can think about competition between Androids and Apple products. These are two big players in the market. There's not an infinite number of firms, neither is there a single monopoly which is producing everything. You can also think about the market for search engines. Well, Google is definitely a big player, but there's also big players from China. There's some other big players, one or two other big players that you could name. But the idea is that you can always think about cases where you don't have a single firm, you don't have an infinite number of firms, you have two, three, four, five, maybe 10 firms. What does economics have to say about firm competition when there are these one, two, three, four, not one, two, three, four, or 10 or 50, a finite number of firms? How should we think about firm competition in that case? So it turns out there are two simple ways in which we can talk about firm competition. Number one is Cournot Nash, and number two is going to be Bertrand Nash. Okay, and they have Nash in their names because the idea of the equilibrium there is going to be based on Nash equilibrium, which we already studied. In fact, this was one of the primary motivations for why we studied Nash equilibrium, because we wanted to get to a point where we can talk about firm competition. A big chunk of this class is based on production theory, and we want to talk about firm competition. Okay, then, so let's start with Cournot Nash. Okay, so Cournot was a person. In fact, this person was a French mathematician who was writing in the first half of the early 1800s, the 19th century, in fact. Okay, and he was already thinking about a way of modeling firm competition. The interesting idea is he came up with the idea that if you want to model firm competition, you might want to settle on an idea of equilibrium where all the firms are best responding to each other. Okay, so he was already talking about mutual best responses in 1838, which is super interesting because Nash is writing his thesis around 1940s, 1950s. So this is more than 100 years ago. And there was someone in France who was already thinking about an idea which was very close to that of Nash equilibrium. Remember, Nash equilibrium is about mutual best responses. Cournot himself is also talking about mutual best responses. He's talking about it from in a limited setting. He's only talking about it in terms of firm competition, in terms of firms competing against each other. But the idea he's going to give is going to be that of a Nash equilibrium, because he's going to talk about, as I said, mutual best responses by firms. And in 1838, he's already publishing his work. Okay, and that is, I think, one of the coolest things that you can think about. That there was this revolutionary thing that changed multiple streams of, multiple disciplines: economics, political science, biology, which was this idea of Nash equilibrium and game theory. There were people 100 years ago, before even the idea was born, who were already thinking along those lines. Okay, and Cournot was one of them. Now, here is how Cournot's setting look like. So Cournot said that there are going to be a particular number of firms. Okay, they're going to compete. So just like in a game, they're going to decide what actions they're going to take, and because it's firm competition, the actions are going to be either quantity or prices. And in fact, Cournot-Nash equilibrium, and you should always remember it, it's a model of quantity competition. So firms are going to compete in the dimension of how much they produce. So it's a model of quantity competition. Okay? So this is going to be like a game where each firm decides how much to produce. So the strategy for each firm is going to be the quantity that has to be produced. So strategy is the quantity. So you can think of this as a game, just like any other game theory. It's a game between firms where they decide how much to produce. The strategy or the action space is quantities. Now, how does one firm affect the other firm? Well, one firm affects the other firm because the quantity that you produce, if you produce a lot of quantity and then flood the market, that's also going to affect me when I try to produce my quantity. Let's say, let's think back to the problem of United Airlines and American Airlines. They were thinking about how many flight passengers to fly in a week, in thousands of passengers. This is a problem we solved in the game theory classes. Okay. And we were talking about if one of these airline companies flies too many passengers, that brings the prices down for the other airline company too, because they are creating a huge supply, and with the higher supply, prices go down. That's exactly the mechanism here. Each firm is affecting the other firm because depending on the quantity they produce, the total market price changes, and that affects the profits of every other firm in the market. The Cournot-Nash equilibrium is going to tell us in a situation like this, what is the amount of quantity we would expect firms to end up producing. That is the idea of Cournot-Nash equilibrium. So let's go to a simple problem directly, and you'll see what I mean by this. So we're going to look at three cases, and each case is going to kind of build on the previous one. So case one is going to be the case of two firms who are competing against each other, and they're going to sell undifferentiated products. What does this mean? They're going to sell exactly the same thing. Exactly the same thing. Okay. And then, there is a total market demand curve. This is the demand curve for the whole of the market. So what this says is the price here goes down as long, it depends on the total amount produced by these two firms, right? It's A minus B times Q, where Q is the total amount produced by these firms. So this is the demand curve, okay? So here is the point where you should pay close attention. What this is saying is, well, clearly each firm is going to affect the other firm's price, because both of these firms are going to have to use this price when they sell it. And clearly, even if you're firm one, firm two's quantity does affect the price that you face, which means that it does affect the profit that you could get. So any firm's outcomes or profits depends on what the other firm is doing. That is completely in the realms of game theory. Okay. Now we have had some, simplifying conditions. Let's say, the marginal cost is C and the fixed cost is 0. That just makes our lives simple. And suppose we are asked to find out what is the equilibrium outcome of this market. So if you think about it, this question is kind of simple. All it says is there are two firms. They're selling identical products. There is, a demand for the market and, the price. I mean, this is basically the inverse demand. The price depends on the quantities produced by both the firms. And it's that equation right there that you can see on the screen. The question is, could we find an equilibrium for this market? Okay, and if you know how to solve this problem, you'll find it pretty easy to solve all the other problems that are going to come up later in this lecture. So let's start by trying to solve this problem. So let me go to the whiteboard. So what we have is two forms. Let me write down the problem first. Let's use black ink for now. So we have two forms, and the aggregate demand curve is P equal to A minus B Q1 plus Q2. The cost of production for both the forms is going to be C times Q, because that's the marginal cost, and there is no fixed cost. Okay. The question is, how much are these firms going to produce, and what is the equilibrium price in the market? Okay. So you have to find out. So what are we going for? We're going for what is Q1 in equilibrium going to be. This is equilibrium production by Q1. This is why I put a star on its side. What is the equilibrium production of Q2? So Q2 and a star on its side. And what's the equilibrium price? That is the question. So here is how you solve this problem. You always start by writing down each firm's profit maximization problem. So let's say we're trying to find out firm one's profit maximization problem. And let's do this step by step. Let's call this step one of solving these problems. So step one is finding firm one's profit maximization problem. So how are we going to do this? We write down, okay, firm one's profit. Let's call it pi one, because pi is for profit, and because it's firm one's, we call it pi one. So pi one is going to be, as you would expect, it's price times the quantity firm one is going to produce minus the cost of production. C is the marginal cost, there is no fixed cost. So that is what it's going to be. And we know that the price is nothing but A minus B times Q1 plus Q2. And then there is a Q1 multiplied with this whole thing here. And then there is a minus CQ1. All we have done here is we know that the price can be written as, this whole term right here. Okay, then. So now we have to figure out what firm wants. Remember, the idea of finding Nash equilibria is you have to find both firms' best responses. So somehow you have to find firm one's best response. So step two is going to be find firm one's best response. What does best response mean? It means what is firm one going to do? Remember here, it's quantity competition. So each firm's best response has to be some amount of quantity, because both firms are trying to decide on a clever amount of quantity in this competitive market. So firm one's best response has to be some optimal quantity for firm one based on whatever firm two's quantity is. Okay. So, just a reminder, and because it's a reminder, I'm going to put it on top and in a different ink. Remember, this is Cournot competition, which means it is quantity competition. And each firm's action is, which means that each firm's action is basically their quantity. So best response basically says what is the optimal quantity for firm one to produce, given whatever action firm two is doing, and action by firm two means firm two's quantity also. So then firm one's best response means that what is firm one's optimal production given what firm two is producing, okay? That is what it means. Let me write it down so that you remember it. So this means what is firm one's optimal quantity given what firm 2 is producing. Okay, so let's continue on this other half of the whiteboard. So how are we ever going to find this? It's not too difficult actually. So what firm 1 is going to do is, let's also continue it here. Firm 1 is going to think about, okay, let me think about my profit function. What is the best I could do? Well, the quantity for me that does the best for me in terms of my, for maximizing profits, the derivative of my profit must be 0 at that point. Okay. If you want to maximize profit with respect to your action is the quantity. Then what do you want to do? You want to take a derivative of the profit with respect to the quantity, which is exactly this. So then how do you figure that out? Well, let's write down the profit. The profit is AQ1 minus BQ1 squared minus BQ2Q1. And there's more. So it doesn't just end there. Let me remove this and let me write down what else we have. We have a minus CQ1. That's the whole of the profit. That has to be differentiated with respect to Q1 and has to be made equal to 0. Okay, so if you take the derivative, you get A minus twice BQ1 minus BQ2 minus C is 0. And if you do a little bit of math, and you know, this is kind of something you could do at home, you'd figure out that Q1 is going to be A minus BQ2 minus C divided by twice B. This is just solving this from this. It'll take you a couple of steps maybe, but you'll get that. So that is form one's best response function. This thing right here, and you should remember this. It's time to use a different thing so that you remember this. This is what we found right here is form one's best response function. Why? Because this is the Q1 that maximizes firm one's profit for any value of Q2, which is firm two's action. So whatever firm two's action is, I can use that equation, and for that amount of Q2, it's going to tell me what as firm one, it's going to tell me what's the best thing I could do. So that is my best response function. Okay, so then you get this equation. Now, how do we find? Okay, so that is firm one's best response function. We need to find both players' best response function, and they must be mutually best responding, right? So step 3 is going to be, and maybe it's time to go back to black, is going to be find form 2's best response function. Okay, so find form 2's best response function. So how would we do it? Well, firstly, we have to follow the same steps. We have to write down form 2's profit. Form 2's profit is price times the quantity produced by firm 2 minus the cost. Well, the price we know comes from this equation right here, A minus B Q1 plus Q2. Then that times Q2 minus C times Q2. That is firm 2's profit. What is firm 2's best response function? How do we find it? Well, firm 2 must be trying to maximize her own profit with respect to the quantity she's producing. So that means this must hold. If that holds, then we can take this derivative right here and put it to 0. But let's take the derivative. You're going to get A minus twice B A minus B Q1 minus twice B Q2 minus C, and that is going to be equal to 0. This is just coming from this derivative. We know what pi 2 is. Put down that pi 2, take the derivative, you're going to get this. I want you to solve this derivative right now. Pause the video, solve the derivative, and make sure that you get exactly this. Okay? If you get that, then you should also be able to get that firm 2's best response is Q2 is equal to A minus BQ1 minus C divided by twice B. That is going to be firm 2's best response. This is firm 2's best response. And all we have done is we've taken the derivative of firm 2's profit, right? We got this equation, and then we have done the math here. All we have done is we've changed sides and written down Q2 as a function of everything else. That's all we've done. And again, try and do the math. Try and get from here all the way to here, right? Try and do this math. It's going to be extremely useful for you on the exam and also the next assignment. So you want to do this on your own. Okay, so let's assume that you did that. Now, what do we have? What we have is firm 1's best response and firm 2's best response. So this is what we have. We got firm 1's best response. And that was equal to, and that gave us Q1 is equal to A minus BQ2 minus C over twice B. And this is coming from the last page, or you can think of it as the last slide. We already figured that out from the last slide. And then here we also derived Q2 is equal to A minus BQ1 minus C over 2SB. This is from 2's best response. So from 1's best response, from 2's best response. Question is, how do we find the Nash equilibrium? Well, at the Nash equilibrium, both forms must be best responding to each other. So both of these two equations must hold simultaneously at the Nash equilibrium. Let's write that down. Both these equations must hold simultaneously at the Nash equilibrium. Okay. Because at the Nash equilibrium, both forms must be best responding. That's just the definition. Every player best responds to each other. Well, then if every player is best responding to each other, both these equations have to hold. And they have to hold simultaneously. So, this has to hold and this has to hold. So how do we figure out points where two equations hold simultaneously? We solve them. So that gives us step 4. Step 3 was finding form 2's best response. Step 4 is solve for the, let's say, solve these two best responses. That might be the easier way to say it. Solve these two best responses. Let's go to the next page. So what you have is Q1 is A minus BQ2 minus C over 2. And you have Q2 is it twice B, A minus BQ1 minus C over twice B. Okay, so you've got those two equations. Now, I want you to think about what do you think is going to be the solution to this problem? So how would you solve this? Think about it. How would you solve these two equations, right? And if you want, you can pause the video, that's fine. But I want you to think about it. It's important. Okay, how would you solve? Basically, if you think about it, you have two linear equations, right? Two equations which are both linear. And there are two unknowns, Q1 and Q2. How will you solve it? Well, the idea is, there are many ways to solve it. One of the easiest ways to solve it is by the method of substitution. So let's substitute Q2 into this equation. So what we're going to get is Q1 is A minus B, substituting Q2. Q2 will be written as this big whole thing, A minus B, Q1 minus C over twice B. There is a minus C, and then there is a divided by twice B. Okay, so let's keep going. Let's multiply both sides by twice B, making life easier. So that will that will give us 2BQ1 is equal to A minus half of A minus BQ1 minus C, because these two B's cancel out. So this becomes A minus BQ1 minus C half. Now multiply both sides by 2 again. That's going to make our lives easier. So that becomes us 4BQ1 is equal to twice A minus BQ1 minus C minus twice C, multiplying both sides by 2. Okay, the right hand side becomes twice A minus A plus BQ1 plus C minus twice C. Okay, so then what do we get? Well, you can simplify this and you're going to get thrice BQ1 equal to A minus C. And then you would get Q1 is equal to A minus C over thrice B. Okay. Now, once you're there, you basically have everything. Okay, you found Q1 is equal to A minus C over thrice B. Only thing that's remaining is to find Q2. Think about how should we find Q2? What do you think it's going to be? Pause the video, think about it. So Q2, all you have to do is you have to um, take this equation right here. Q2 is A minus BQ1 minus C over twice B, and replace Q1 with what you found, which is Q1 is equal to A minus C over twice B. And if you solve that, you're going to get A minus C over thrice B again for Q2. So both Q1 and Q2 are going to be equal in equilibrium. So the way we write down the solution to this problem is that the Cournot-Nash equilibrium, and this is just the shorthand for equilibrium, EQM, is that both forms are going to produce the quantity equal to A minus C over thrice B. And the price, you can figure out what the price is given these two quantities. Okay, you can find out that price. Let me leave that as an exercise for you. That is a solution to the quantity computation problem within two forms. There's two forms. Now there is a lesson here. Okay, and this is a nice and a crucial lesson. The lesson here is if you have two forms, three forms, if they are identical, then they are going to, in equilibrium, they're going to end up producing the same amount. In fact, it's so important, I want to write it down. And let me write it down here, and let me use a different ink here, okay? So that you remember this. So there is a lesson here. Of course, we found out how to solve the problem, but the lesson here also is with symmetric forms, like the ones we had two forms who were completely symmetric. They had the same cost function. So with symmetric forms, and here it means they have the same cost function and they're facing the same demand curve, right? The equilibrium actions are identical. They're going to take the same action in equilibrium. As you can see, they did take the same action in equilibrium. It's quantity competition, so actions basically mean quantity, and they produce the same quantity. Okay, so that's a good trick to know. So now that we are here, and now that we have this insight of symmetry, now we can solve a more complicated problem. Okay, so let me take you to the next case. So let me quickly take you to the slides, and we'll be back at the blackboard super soon. So let me take you back to the slide. So the first case that we did was Cournot-Nash equilibrium with two forms and undifferentiated product. They were selling the same thing. Okay, and we just finished talking about it. So this was just case one that we did. This was case one. So let's do case two now. Case two is going to be the following. So previously we had two forms. Suppose we say there are some n number of forms where n could be any number. It could be 2, 3, 4, 5, 6. Name your favorite number. N could be anything. They're all selling undifferentiated products. Can we find out a general solution to this problem? Now, in a way, this class is special because we haven't been solving for general solutions to equilibrium yet. This is the first class where you're seeing it. So in this class, you're going to learn certain techniques that you haven't seen before. And if you ever end up doing, if you ever want to go for grad school in economics, right? These are certain tricks that are going to come in extremely handy. Even if you never go to grad school, but if you enjoy math, even then it's going to come in handy because these are nice tricks and they are useful in many situations, not just these problems. So think of the problem once again. It's very general. It's saying that we are not even using numbers here anymore. There's an n number of forms where n is an abstract number of forms. It could be 50, 100, 20, I don't know, whatever the number you think, you want to solve it for. The demand curve is also has just got to do with abstract numbers. Price is A minus B times Q. And because there are n forms, right, Q is just the sum of the products from the n forms. Okay, and remember the symmetry trick that I just taught you, that's going to come in handy here. And you'll see it's a really nice trick. So how do we solve this problem? Well, here is how you would solve this problem. Let's go back to the whiteboard. Now we are doing a slightly more difficult looking problem. What we have is n forms, and the demand curve is given by P equal to A minus BQ. And let's say the cost function still is C times Q. There's no fixed cost. How would we solve it? It will turn out that the symmetry trick is going to do everything for us. So here is how you would do it. Take any forms problem. Let's think about form one's problem. What is form one's problem? Well, each form is in the business of trying to maximize profit. So for form one, what form one tries to do is trying to maximize its own profit. So what is form one's profit? That's P times Q1, that's the revenue, minus C times Q1, that's the cost. So that's the profit. Well, what is P times Q1? Well, P now is this complicated thing because it's A minus B times, let's do it step by step, A minus B times Q times Q1 minus CQ1. Now, what is A minus B times Q? Well, Q is basically the sum of everyone's quantity. And there are n forms here. So then that is what Q really is. It's kind of a complicated object, right? And interestingly, what you would figure out is that from one's quantity Q1 is also in here because this Q has everyone's quantity. So definitely it has from one's quantity also. So that is pi 1. And if you want, you could simplify it a bit further. What you're going to get is you get A times Q1 minus B Q1 squared minus B Q2 Q1 minus B Q3 Q1 all the way up to minus B Qn Q1 minus C times Q1. That is going to be for one's profit. And you want to pause the video and think about the multiplication I just did. All I've done is multiply it term by term. The first term is Q1. This is why there is a Q1 squared, because you're multiplying with Q1 outside and Q1 inside. Every term after that is Q2, Q3, Q4, all the way up to Qn. And when you want to multiply them, you get B times minus B Q2, Q1 minus B Q3, Q1, so on and so forth. The last term is going to be minus B Qn, Q1, and then there is the minus CQ1. That is just the whole math. Now, what is firm one trying to do? Firm one, like every other firm in this market, is trying to maximize its profit. So the question really is, and what is firm one's best response function? That is what we should be after. What is firm one's best response function? Firm one's best response function is going to be something where firm one tries to best respond to everyone else. There's n minus one other people because there's n forms. If you take out firm one, there's n minus one others, n minus one other forms. And firm one is trying to best respond to every other form out there. So that's a complicated problem. So if you try and figure that out, what you're going to do is, okay, so basically what firm one has to do is, firm one cannot control anyone else's production, but firm one can control her own production. And firm one is going to try and do the best she can with respect to her own action, her own production. So what that means is she wants to do d pi 1 dq1 is equal to 0. That's what she wants to do. So let's try and figure out what d pi 1 dq1 is going to be from here. What you're going to see is if you take a derivative, let's do it term by term. The first term after taking a derivative becomes a. The second term becomes minus twice bq1. Third term is going to become minus bq2. Fourth term is going to become minus bq3. I'll keep on going. This term right here is going to become minus bqn. And then there is this minus cq1, which becomes minus c. And then that is equal to 0. So that right there is going to be firm one's best response function. We don't know how many terms there are in between. It depends on what the n is. But for however many n's you have a BQ2, BQ3, all the way up to BQN. There's a minus C, and there's always a minus 2 BQ1. Okay. Okay, then. So now, ideally, in the ideal world, we would find out every firm's best response function and then trying and see if we can solve those n equations. When we had two firms, we found both firms' best response functions, and then we tried to solve those two equations. Now we have n firms. So if we didn't know any better, what we'll try to do is we'll try to find n firms' best response conditions, n firms' best response functions, and try to solve that. That would be pretty, that would be pretty complicated. We don't want to do it that way. There is a trick. The trick is to remember that every firm here is symmetric. They have the same marginal cost. They're operating in the same market with the same demand curve. Given that, okay, what we know is in equilibrium. So okay, this is the symmetry trick, and let me write it down here. We're going to talk about symmetry, which basically says all the n forms have identical marginal cost and face identical demand curve. Let's just say price, identical price. The price is the same for each one. Okay, so the cost is the same, the price is the same. And what that means is, right, symmetry implies that in equilibrium, they must produce identical quantities. That is what symmetry implies. They must be producing identical quantities. So what that means is we have that one equation already. We have a second equation, which is going to be super powerful. The second equation is going to say that in equilibrium, Q1 is the same as Q2, is the same as Q3, is the same as all the Qs, all the way up to Qn. That is our equation 2, which is a super powerful equation. It says all these quantities are equal. Once we have that, we are pretty much in the game of solving this super quickly. Let me show you how. Let me remove this stuff so that we have enough space. We're going to go up top from this line right here. So what we are going to do now is, now that we have this insight, that all the Qs are equal, you know, let's think about how many Qs there are. And we want to do it this way. So let's think about it. So this goes from 2 to n. So think about all the terms here. Let me just, you know, write down this whole equation first. So you have a minus twice bq1 minus bq2 minus bq3 all the way up to minus bqn minus c is equal to 0. The insight is that all the q's are equal. When all the q's are equal, what we understand is that this q2 can be replaced by another q1. This q3 can be replaced by a q1 also. This qn can also be replaced by a q1. All of these quantities can be replaced by q1s. That is what it tells us. So then what happens is this bq2 becomes a bq1, a bq3 becomes a bq12, bqn becomes a bq12. Okay. Everything has become a bq1. Can you solve it there on? Well, okay, so how will you solve it? Well, the a comes down unchanged. The minus, now let's think about what is the addition of all of these terms. That is what we need to figure out. And that's equivalent to finding out, you know, how many bq1s there are. The easier trick to do here is, let's write down the first two terms the same. So then there is this minus twice bq1. Let's write down the minus twice bq1. Then you have minus bq1, minus bq1, minus bq1. All of them are minus bq1s. How many of them do you have? If you go from 2 to n, when you write down 2 to n, how many terms do you get? 2, 3, 4, all the way up to n. you get n minus 1 terms. Why? If you had started from 1, you would get n terms from 1 to n. If you start from 2 and go all the way to n, you get n minus 1 terms. So basically from q2 to qn, you basically have here n minus 1 terms. You have n minus 1 terms. And if each of them is minus bq1, then in total what you have is n minus 1 terms bq1. And there is the minus sign in front of it. Then you have the minus c, and that is equal to 0, and you're done. Okay, so that was the trick. There is some math here, and the math is kind of nice and fancy, but it's not difficult. And you want to pause here and think about it a bit more. All we have done is we have thought about BQ2, BQ3, all the way up to BQN. All of these Q2, Q3, Qn, they are equal to Q1 because of symmetry. All of these quantities must be equal. If they're equal, all of them become BQ1. So this is a BQ1, this is another BQ1, this is another BQ1. How many of these are there? Well, we know that these go from Q2 to Qn. That means that you're going from 2 to n. How many terms do you have when you go from 2 to n? You get n minus 1 terms. If you had started from 1 to n, you would have had a total of n terms. When you start 1 later, so when you start from 2 to n, you get n minus 1. So then there are n minus 1 of these terms, each of them equal to bq1, and then there is the minus c. Okay, then, so now let's take the next step. Let's make some space. Let's take the next step, and we'll be done with this particular case of Cournot-Nash equilibrium. Let's remove this. Okay, now we'd have enough space. So back to the problem. So then what is this? So we have a minus twice bq1 minus n minus 1 bq1 minus c equal to 0. So what that means is that a minus, now we are going to add these two up, these two terms up, and that you would see is going to give you n plus 1 twice, sorry, there is no twice, there's a b, there's a q, there is a 1, minus c is equal to 0. And that looks a bit untidy, so let me just clean it up. All we have done is we have added these two terms up, twice bq1 and n minus 1 bq1. If you add them up, you would see you're going to get this term right here. Then what that tells you is n plus 1 bq1 is equal to a minus c. So then q1, which is what form 1 is going to produce when there are n forms competing against each other, is a minus c divided by n plus 1 times b. What are the other forms going to produce? Well, by symmetry, every form produces this quantity. So we know that basically q1 and q2 and q3 and all the forms there are all the way up to qn, all of them are going to produce a minus c divided by n plus 1 times b. That is going to be the quantity produced by each form here. Now, there is another really pretty part of the math, which is possibly my favorite part of this problem. I'll tell you why. I mean, I'll try and convince you that it's very pretty, and let's see if I can. So if that is the quantity being produced, then you know what is the price? The price is a minus b times total quantity. Well, the total quantity is if every form is producing this much and then there are n forms, then the total quantity is n times a minus c over n plus 1 times b. Now, you know, you can do a bit more math here, but you know, let's not do that much more math. Let's just write it down as a. So this b cancels out in the numerator and the denominator, and you get a minus n over n plus 1 times a minus c. That is what you get. That is the price in a market with n firms who are competing against each other. Now, here is a beautiful part of the math. I mean, there are a few beautiful parts of this. Let me tell you the first one, which is the easy one. One way to know we have done this correctly is that we had already solved the problem for n equal to 2. When there are two firms, we already found out Q1 and Q2. Now let's see if we get the same answer when we plug in n equal to 2 here. When n equal to 2, you will get Q1 is equal to Q2 is equal to, plugging in n equal to 2 here, you get A minus C over thrice B. Boom, that's the same answer we got last time. That's good. So it means, the math works. The even nicer part of the math. And if you remember, limits and calculus, then this will work a bit better. So think about n firms. Think about what happens when n goes to infinity. Suppose there are n firms that are competing among each other. The market price in Cournot equilibrium is this. What happens to the market price when n goes to infinity, when the number of firms that are competing steadily keeps up rising all the way up to infinite firms? Now, we already know that when there are infinite firms, then price has to be equal to marginal cost. But that is something we have never established mathematically. We have never mathematically, with an equilibrium concept, established that price has to be equal to the marginal cost. Here, we're going to do that. Remember, we're doing all of this in a Nash equilibrium concept. We're going to derive why, as n goes to infinity, price goes to marginal cost. So, okay, how are we going to derive it? So maybe go to the next page. What we have is the price was equal to A minus n over n plus 1 times A minus C. If n goes to infinity, then what happens? N over n plus 1 is nothing but dividing both numerator and denominator by n, you get 1 over n. So limit n tends to infinity, n over n plus 1 has to be equal to 1, because what's going to happen is this n is going to infinity. So this term right here goes down to 0. So that's just 1 over 1. So that's 1. So as n goes to infinity, so if n rises all the way to infinity, price is going to go to A minus n over n plus 1 is going to go to 1. This goes to 1. And then it has A minus C multiplied to it. So this is A minus 1 times A minus C, which is A minus A plus C, which is C. Voila. We just derived using Nash equilibrium concepts that if the number of firms with quantity competition goes up to infinity, then the price in the market is going to converge to the marginal cost of those firms. We didn't have to know what you've learned under perfect competition. Cournot, just by his method of finding Nash equilibria across competing firms, could show you how to derive that from first principles, and that is something beautiful. I mean, that's really something. Okay, so that's kind of one of the very cool things about Cournot Nash equilibrium. Okay, then, so then we solve that. Let me do a third case now. So we are still in the world of Cournot. Let me go back to the slides. We just finished case 2, which was finding n forms undifferentiated products. Case 3 is actually very simple, so I don't want to separately do the math, but I want you to think about it a bit. So suppose there are two firms, but they're selling differentiated products. Differentiated products means that they're not exactly selling the same thing. They're selling something that's slightly different. I mean, we go back and forth on this example, but I mean, think about Coke and Pepsi. They're pretty similar, but they're not exactly the same thing. Some people do have a preference for Coke and some people do have a preference for Pepsi. Clearly, the difference in them is small enough that if one of the firms slashes, if one of the firms produces too much or one of the firms produces too little, that's going to affect the demand of the other firm. So clearly, there is some connection between these two products. So if one of the firms produces a lot of Pepsi and floods the market, that's going to affect the demand of Coke. But they're not exactly the same thing. And the way we model that, so this is just a slight change of the first model we saw, is that we say that the first firm's demand is something like this. Um, so firm one's demand, so the price that it faces, depends on its own quantity, depends on the other firm's quantity, but the amount by which it depends on its own quantity is bigger than the amount by which it depends on the other firm's quantity. That is how we model differentiated products. So once again, how do we model differentiated products? The idea is simple. The idea is we always think about, in the previous case, what we had is for both the firms we had previously, let's use a different thing so that we know we're talking about the previous case. We had the price for both firms was A minus BQ1 minus BQ2 because they were selling the same product. When you're selling similar but slightly different products, okay, so we're thinking about similar but differentiated products, then you don't have the same coefficients on the amount produced by yourself and the amount produced by the other firm. Rather, your price depends more on how much you produce than it depends on how much is produced by the other firm. And that is captured by B1 being the bigger term and B2 being the smaller term. And then, both of them are greater than zero because when the other firm produces more, your price definitely goes down because now fewer people buy from you. So that's why B1 and B2 are positive. Now, how would we solve a Cournot problem like this? Exactly the same way. So let me give you some hints for this also. So let's see what's a problem we can solve. Um, let me pick up a problem from the lecture notes. So let's say, okay, so I know what to do. So let's say we have the following numbers. So there are going to be two firms and they're going to be selling similar but differentiated products, okay? And let's say that let's take, actually let's just take a problem from the problem set itself. So let me find out the problem set so that I can directly solve the problem from there. So let's take this problem directly from the problem set, and let's try and solve it then. So suppose that there are at least two firms, okay, and they are doing this price competition where they're selling these differentiated products. So let's say the two firms are, let's say it's Firewings and Wingstop. So they are these two stores that sell chicken wings, okay, and this is from F and this is from W. So chicken wings in both of these two restaurants are, chicken wings are chicken wings, so they are very similar, but they might have different seasonings. So maybe they are slightly differentiated, even though they are similar. So they're not exactly the same product. So let's say that the firms face the following demand. So for firm F, it's 112 minus QW minus 0.5. Okay, so there's a typo here. let's say for form F, this is the demand faced by firm F, which is fire wings, and the demand faced by firm W, let's say it's going to be equal to 130 minus QW minus 0.5 QF. Very good. So let's say this is the problem that we have. This is a problem of differentiated Cournot production. Differentiated Cournot competition. And we have to figure out what is going to be the Cournot-Nash equilibrium in this market. Let's also talk about the marginal costs. And let's say the marginal costs are equal to 5. So let's say that the firm space and marginal cost equal to 5. So how is someone going to solve this problem? Well, let's think about Fire Wings problem. So what Fire Wings thinks about his or her own profit. So pi F is going to be the price. The price is 112 minus QF minus 0.5 QW. That's the price. Multiply it with the production done by Fire Wings minus marginal cost times production. There's no fixed cost. So that is Fire Wings profit. So that's going to be 112 QF minus QF squared minus 0.5 QF QW minus 5 QF. Now, the next step is going to be figuring out Fire Wings' best response. And we always do it the same way. We have to take a derivative. Okay, so if we take a derivative, we're going to get 112 minus twice QF minus 0.5 QW minus 5 is equal to 0. That is Fire Wings' best response. The idea always is you want to figure out both the firm's best responses, and at the Nash equilibrium, they must be best responding to each other. Well, to have that, now the next step has to be trying to figure out Wingstop's best response. Okay, so let's do Wingstop's problem. For Wingstop, the profit is by W is 130 minus QW minus 0.5 QF. That's just the price, multiplied by quantity produced by Wingstop, minus, let's say, the cost of production, which is 5 times QW. Let's separate these two so that things are clear. And let's use a different ink to also make life easy. Here we go. So then you want to figure out, the best response function, which is pi of QW differentiated with respect to the quantity. This has to be equal to 0. So if you take the derivative, right, you're going to get 130 minus twice QW minus 0.5 QF minus 5 is equal to 0. So then you get these two best response functions. One is this one and one is that one. Both of these are equations. So that is the first equation. That is the second equation. And all that remains to do is to solve for the best responses. So you solve for these two equations. Solve the two equations to find QF and QW. And of course, the solution would exist because these are two equations with two unknowns. These are linear equations. So I'm not going to solve these equations for sure. That's part of the homework, but you should be able to solve it. Okay, and one trick that always works while solving linear equations, two unknowns, two equations, is substitution. Find the value of QF from one of the equations, substitute it in the other equation. That's the clue. You do it, you're going to find QF. And then you can use that to find QW. Okay. So then we did 3 cases under Cournot competition. The first one was 2 firms, undifferentiated product. The second one was n firms, undifferentiated product. And we used a trick there. Okay, we used a trick. And the trick was that Um, the trick was actually pretty simple. We realized that in symmetric problems, forms end up producing the same quantity. And because it's undifferentiated product and because all forms have the same marginal cost, we knew that every form would end up producing the same quantity, and that was it. And that just helped us solve. Then the third case was when it is not undifferentiated product anymore. Rather, it's a differentiated Cournot competition. What that means is that different forms are going to produce things that are going to be slightly different. And if they produce things that are slightly different, then, right, then you can't use the symmetry trick anymore. That's kind of what this problem is. You can see that now each form faces a slightly different demand, and the coefficients on its own quantity versus the other guy's quantity is not the same. But the trick is the same, right? We find out both forms' best responses and then solve for those two equations, and that's it. That does the trick. Okay, so that's going to be it for today's lecture. Okay, and we'll pick up. We'll try and do Bertrand next time. The one thing that I tell you is that you really want to solve these problems by hand, because solving them by hand is what is going to make you good at them. Okay, so that's it, and I'll see you guys soon. Take care.